Next, we are going to study about the color in the coordination complex. Okay, we know a substance appears colored when it absorbs light at specific wavelength in the visible part of the electromagnetic spectrum. What is the visible part? It is about 400 to 700 nanometer and transmits or reflects the rest of the wavelength. Each wavelength of visible light represents a different color. White light, such as sunlight, is a combination of all colors. An object that absorbs all visible light appears black, isn't it? We know that when the all color are reflected, then it will appears white, and if it absorbs all colors of light, then it appears black, right? When the energy of photon h nu is equal to the difference between the lower and higher d orbital energy levels, an electron is promoted from a lower energy to higher energy. Okay, that is when an energy equal to the difference between the lower and higher d orbital energy will strike on the electron. It will get excited from ground state to the excited state. From low energy level to high energy level, it will get excited, isn't it? Then if the wavelength of the photon absorbed by an ion lies outside the visible region, then the transmitted light looks the same as the incident light, white, and the ion appears colorless. Okay, thus due to DD transition, because of splitting of d orbitals in presence of ligands, complexes formed, then that is why they appeared colored. So how this how this coordination compounds shows colored? It is due to the DD transition. This coordination complex appear colored. Okay, that is when the ligands in the presence of ligands, the complex formed, there is splitting of d orbitals in it, isn't it? Due to the presence of the ligands, there will be splitting of d orbitals into T2g and EG orbitals. Okay, so when the light falls, what will happen? Electrons in the T2g orbital, they get excited and get promoted to the EG orbitals. Okay, this is in case of octahedral complex. We know that in the octahedral complex, the T2g orbitals, it lies in the lower energy, and EG orbital, it has a higher energy, isn't it? So the electrons in the T2g orbitals, they will get promoted to the EG orbitals. Okay, so this due to this DD transmission, the complexes formed shows color. Okay, so the experiments with the coordination compounds have revealed that for a given metal ion, some ligands causes a small energy separation of d orbitals, whereas others causes a large separation. That different ligands may bring different colors to the complex ion of the same metal ion. We know that in case of strong field and weak field, there is difference in the splitting, isn't it? So the T2g and EG orbitals, their distance is different in a strong and weak field, isn't it? So the energy of the photon absorbed, it will be different in case of different ligands. So the color exhibited by the ligands will be also different. Okay, so what is the reason for the color in the coordination complex? It is due to the DD transition. Next, we are going to study about the limitations of crystal field theory. Crystal field theory is successful in explaining the formation, structures, color, and magnetic properties of coordination compounds to a large extent. But it fails to account why ionic ligands, which are assumed as point charges, produce low magnitude of crystal field splitting. That is, they act as weak field ligands in the spectroscopic series. Okay, we know in the weak field there is Br minus, I minus, they act as a weak field, isn't it? Then this crystal field theory, they are not successful in explaining why these anionic ligands act as weak ligands. Okay. Then the crystal field theory, it does not take into account the covalent character of bonding between ligands and the central metal ion. Okay, so these are the limitations of the crystal field theory.